Hey guys, welcome back. We're going to start on these notes for the central limit theorem. You can call this central limit theorem part 2. We're going to be actually looking at applications of the central limit theorem today. So like what kind of problems can we solve now? How can we use this? What can I expect to see on the quiz or the test? So that's what we're going to talk about today. So you might want to recall from yesterday, just a quick summary from the last section of notes that we did. We talked about that central limit theorem, and I'll kind of put the summary that we did yesterday back up here. We talked about what happens with the shape, and we said if that sampling distribution had a sample size of greater than 30, the distribution would normalize. And it could also happen, you don't have to have a sample size of 30 or more if the original population was already normal. All right, so the shape will normalize if either one of those two conditions are met. All right. We talked about the center where the mean of the population and the mean of the sampling distribution stayed the same no matter what the sample size was, and the spread reduced, right? So as the sample size increased, the standard deviation decreased, right? And we could calculate that new standard deviation using this formula. So we're going to take a look at some problems that kind of use this theorem and see what we can do here. All right. So let's read through this one carefully. It says, in 2018, all juniors in high schools across Illinois took the test known as the SAT. The mean score for the population of all Illinois high school juniors in 2018 was 1,019 with a standard deviation of 202. The distribution of scores showed that the distribution was skewed right. Okay? So what I did was I took all of that information and I put it down here. Right? We started talking about the population distribution. It was skewed right, so I drew a curve that was skewed right. I marked the center with the mean that they gave me, right? The mean score was 1,019, and I wrote down the population standard deviation, okay? So we got to think about what happened with our experiments yesterday, right? So instead of doing the population distribution, we're going to transition over to the sampling distribution, right? So rather than picking one student at a time, we're going to be picking 10 students at a time and averaging their scores, right? What happens to the distribution in that situation? So if you recall yesterday, we started with something that was skew right, and what happened was the shape still was a little bit skew right, but it started to normalize, right? The sample size isn't quite big enough to make it perfectly normal, but it should start to transition over to more of a normal shape, right? So we're going to see something that is still a bit skew right. So I'm going to draw something like this, and I'm still going to make it a little bit skew right, but less so than what I see over here. Okay. And then I'm going to draw on the mean, right? It should be at the center of the distribution, and that mean is going to remain unchanged. So I'm just going to say it stays at 1,019. Right? And I'll mark that with a mu of x bar, right? Because we're not dealing with the population mean anymore. This is the mean of the sampling distribution. So I have to give it the correct notation, all right? Then we talk about the spread, right? So if you recall yesterday, as that sample size increased, and it did increase, right? It went up to 10, the standard deviation should decrease. So it's no longer going to be 202, right? So to calculate this new standard deviation, I have to take the original population standard deviation and divide it by the square root of our sample size, right? So in this case, this will be 202 divided by the square root of 10. And then I will know what my standard deviation for this is. So I'm going to use my calculator real quick to figure that out. Come over here and I'm going to say, calculator, turn on. There it goes. All right, so I'm going to take 202 and I'm going to divide by the square root of 10. There we go. We got 63.88, let's say. So that'll be my new standard deviation for this distribution where we are taking samples of size 10. So notice the spread of the distribution went down. Okay, so now I'm going to move on. Now the sample size is 30, right? So like I said, what this question is assessing is, do you know what happens as we increase that sample size? Do you understand what the central limit theorem is telling you? Okay, All right, so we know that once we get to sample sizes of 30, that is sufficiently large according to the theorem. So we should get something that is nice and normal. So I'm going to draw a good normal bell curve here. All right, and I'm going to mark the center. So there's my mean, and we know the mean remains unchanged, right? So this is going to be 1019 still. And then I'm going to calculate my new standard deviation here for samples of size 30. So I'm going to take 202 and divide by the square root of 30 this time and see what I get. So I'm going to go back to my calculator. I'm going to take 202 and I'm going to divide by the square root of 30. And we get a standard deviation for the sampling distribution of 36.88. And there we go. Right. So that's how I would demonstrate like what happens. Remember, if it started off as normal, what you're going to want to show as you go through this is you're going to want to show that curve getting skinnier and tighter. So be prepared for a problem like that where it starts off with something that is already normal. Okay. And we're going to see some problems like this too. So like these are the new types of problems that we can now deal with. So let's say we're dealing with the same distribution of test scores. We want to really pay attention to the wording of the problem, okay? So notice in this first one, it says, let's say that I randomly select one student from the population, okay? So we're selecting a single student. And when we select a single student and we try and calculate the probability that they do something, we're going to use the population distribution, all right? So when we take one at a time, that's population distribution, okay? So for this one, right, it does say to include a sketch with a shaded area representing the probability in the calculator input. All right, so I'm gonna take this sketch and remember, so we're taking one student from the population of Illinois juniors. What is the probability that their SAT score is above 1250? So recall that our original population was skew right. Right, and I'm gonna kind of draw this in there. The mean was 1019, and we want the probability that their SAT score was above 1250, right? So 1250 would be somewhere over here to the right. And the probability would be the area under that curve over here, right? Because we want to be above 1250. Well, we can't really do anything with this because we don't know how to calculate probabilities on something that is not normal, right? The population is not normal. So we can't use normal CDF, right? So this is one of those problems that we right now don't know how to solve. We don't really know how to work with distributions that are skew or not normal right now. All right, so we can't actually calculate this probability if we only take one student at a time, right? Now, let's say we change it up. Instead of taking one student at a time, let's say we select 40 students at a time. Okay, so when we take 40 students at a time, we're not dealing with the population distribution anymore. We're dealing with the sampling distribution. And in this case, since the sampling distribution is greater than 30, right? So I'm going to mark that down here. N is greater than 30, right? Because it's 40. We know that the sampling distribution is going to have a normal shape. So I'm going to draw the sampling distribution. I'm going to draw a nice normal curve here. I'm going to mark the center, which we know it remains unchanged. So its mean is still going to be 1019. It's going to be normal. And they want the probability that the mean of the sample, right? What is the probability that this sample of 40 students is going to have a score above 1250? Right, so I can come over here and I'm going to mark 1250. And we want all the scores that are above 1250. So we want that little bit of area underneath the curve on the right. Okay. Don't forget that you need to mark or to calculate your new standard deviation for this, right? So we have to take our original standard deviation, which I forgot. So let me go up here and look at that. It was 202, right? So I got to take 202 and divide it by the square root of 40 first, right? Because that would be the standard deviation of this distribution, not this one. Okay? So I'm going to calculate that real quick. I'm going to take 202 and I'm going to divide by the square root of 40. Oh my gosh. Try that again. 202 divided by the square root 40. And we'll get our new standard deviation here. So we got 31.94. 31.94. All right, so now I can use my normal CDF to calculate that area. So I'm just going to write down the calculator input real quick. So I'm going to go normal CDF. And remember, the first thing they want to know is what is your left boundary. So we're going to say it's 1250. Then they want to know your right boundary. So in this case, it goes off to infinity. So in the calculator, we always do a 1E99 to represent infinity. And then it wants to know the mean, right? So we mark that here. That's 1,019. Oops, I didn't mean to put a parenthesis there yet. And then it wants to know your standard deviation. And this is probably the most common mistake that students make on these problems is that they will put the 202 in there. But remember, this is a sampling distribution now, since we're taking 40 at a time, so they want the new standard deviation, which is 31.94. Okay? And this will get us our probability. So I'm going to go to my calculator, and I'm going to, oops, there we go. I'm going to go to my calculator, and I'm going to run that normal CDF. So I'm going to go second, vars, and normal CDF is option 2. And I'm going to tell it everything it wants to know. It wants to know the left limit, so 1250. And we're going to go here to the upper, which is 1E99. And then its mean is 1019. And the standard deviation is 31.94. And paste. And you'll see like this is exactly what we wrote down on our paper here. So I'm going to go ahead and hit enter and notice the probability that came out, right, gave us a 2.39 with an E negative 13. That's a really small number. So this is a 0 plus, right? We used to write these kinds of probabilities down as a 0 plus. All right, it's not actually 0, but it's really close to 0. All right, so we're going to say 0 plus, and I'm going to write down my answer. I'm going to say the probability that x is greater than 1250 is equal to 0 plus, right? Where x represents the mean of this sample, right? So that's how we can solve a problem like that. So hopefully those two problems illustrate the difference between taking one student and 40 students. You really have to pay attention to the wording of the problem. I'm not going to sit here and say, ding, 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 you have to use central limit theorem. You have to recognize when it's applicable, okay? So make sure you're paying attention to that wording and make sure you think about those conditions that need to be met to use the central limit theorem. All right, and that's kind of what we're going to do here in this next one. So this one says if I randomly select 15 students, okay, so 15 students from the population this time. So we're taking 15 at a time. We're not taking one at a time. And they want to know what is the probability that the mean of the sample is between 12 and 1300. All right, so again, thinking about that distribution, right? So if I have a distribution and this is what we started off with, this was the population distribution, but then I start taking 15 at a time, 15 is not sufficiently large. All right, so we're going to get a distribution. It's a little bit more normal than it used to be, but it's still skew right. It's not what we would consider to be approximately normal. All right, and you can still mark the center. Right, so you can still put your 1019 there, and they want to know the probability that the scores are between 12 and 1300, right? So 1200 would be here, 1300 would be here, and they want this area. The problem is the area underneath the curve, it's not the area underneath the normal curve. So we can't use normal CDF on this yet. All right, so this one, we would just say population not normal. Okay, even the sampling distribution here for 15 would not be quite normal yet. So we can't really calculate a probability on this one either. Okay, so you really got to recognize the different situations, pay attention to the wording, and make sure that you understand when the central limit theorem applies and when it doesn't. Okay, let's take a look at another one here. So we're gonna change states here. So we're dealing with Hawaii now. All right, we're not looking at the distribution from Illinois that was on the first few problems. All right, we're looking at Hawaii. And it says the distribution of the SAT scores was shown to be normal. So the population here is normal. We're starting off with something that's normal. And the mean of this population was 1,087 with a standard deviation of 234. And it says if I randomly selected one student student from Hawaii, what is the probability that their SAT score is above 1400? This one is easy. We've done this type of problem before, right? The population itself is normal. So I'm going to draw that normal curve. I'm going to mark the mean, right? And we got 1,087 for the mean. They want the probability that their score is above 1400. So 1400 is going to be way over here. And we're trying to find this little area. And we can find that area because it's normal, right? So I can say, okay, normal CDF, right? Left bound 1400, right bound 1E99. And we have a mean of 1,087 and a standard deviation of 234. And we can calculate that in our calculator real quick. All right, so feel free to fast forward through me typing this stuff in. We got 1,400, and we got 1E99. I shouldn't have even changed that. Here we go, 1E99, mean 1,087, and standard deviation 234. And we don't have to do that square root thing with this one because it's a population distribution. We're not doing a sampling distribution, so we just leave it alone. And I'm going to go ahead and paste and hit enter, and we get a 0.0905. So I'm going to say 0.091 for probability, right? So the probability x, where x is just the probability of one student, right? So we're going to say the probability that x is greater than 1400 is equal to 0.091. So about a 9.1% chance that someone would score above a 1400 on the SAT in Hawaii. Okay, so let's try it again. Let's do F. And so here it says 25 students, right? So they're taking a sample of 25 students. So we're going to be working with a sampling distribution here. I noticed that right away. From Hawaii are randomly selected. What is the probability that the mean of the sample will be between 1250 and 1350? So I'm going to draw my distribution here. So it is a sampling distribution. And recall, the shape is going to stay normal, right? But it's going to be a tighter curve. It's going to be not nearly as wide or, for lack of better words, fat, right? Like this curve up here. It's going to be a little bit skinnier. Right, but the center stays the same, right? We're still going to have a mean of 1,087, and we want the chances that the score is in between 1250 and 1350. So I'm going to mark those here, and I'm going to shade my area. That's the area that we're trying to find. That's the area that represents our probability, and I'm going to make sure that I calculate my new standard deviation, right? So this is the standard deviation of the sampling distribution. And that is going to be, forget the original one, 234, right? So we're going to take 234, and we're going to divide it by the square root of 25. And you might be asking, well, this isn't above 30, Mr. Weldon. And remember, if the population starts off normal, it doesn't have to be bigger than 30, right? So, but we still have a new standard deviation that we have to calculate, all right? So I'm going to come over here, and I'm going to do 234. Everything, get a new screen. 234 divided by the square root of 25. Enter. And so we got a new standard deviation of 46.8. Like I said, this is the biggest mistake students will make. They will forget to calculate their new standard deviation, and they will skip right to this step where we do our normal CDF without calculating that new standard deviation. All right, so we're going to say left bound this time, 1250. Right bound 1350, and our mean is 1,087, and our standard deviation is 46.8, and this will get us the probability we need. And so I'm going to grab my calculator, and we're going to type that in. So I'm going to go second distribution, normal CDF, and we're going to say 1250 to 1350. Means 1,087, and our standard deviation is now 46.8. Enter. There we go. Look, we got a really small probability. So we're going to say 0 plus on this one. 0 plus. All right. So we're going to say the probability that x is in between 1250 and 1350 is 0 plus. There we go. So we answered that one. Okay. All right, guys. So that's it. Hold on. I didn't mean to hit that yet. I think that's a pretty good array of examples for you guys to work with. I think at this point you should probably go ahead and start working on the homework and practicing some problems with the homework exercises. And I would make sure that you review this video, probably work through a few problems, and make sure that you get ready for the quiz at the end of the week. We'll do a quiz on Friday. It'll have a open time, so you can do it anytime, like any point over the weekend or probably into next Monday. All right.